In the previous video, we introduced the concept of chemical equations. Today, we're going to build on that foundation as we look at stoichiometry. Let's review a few things first. We know that a chemical change is any phenomenon which results in the formation of an entirely new substance. A chemical reaction describes the rearrangement of atoms which leads to a chemical change. Any given chemical substance is identified by the arrangement of its constituent atoms. So rearranging these atoms results in the formation of a new substance, a chemical change. Last but not least, a chemical equation is essentially a mathematical representation of a given chemical reaction, telling us what reactants are reacting to form what products. The central topic of this video, however, is stoichiometry. We can define stoichiometry as the quantitative study of chemical reactions. In simpler terms, how much of each reactant is needed to produce a certain amount of each product. That's what stoichiometry is going to tell us. A good comparison is that of a cooking or baking recipe. No matter what we're making, a recipe is going to tell us two things: the dish we're going to produce, and the ingredients needed to make said dish. We can analogize this idea to chemical reactions by looking at the ingredients as the reactants and the end results as the products. For example, let's say we want to make ourselves a nice bowl of chicken noodle soup. The recipe in front of us calls for 1 carrot, 1 onion, 2 chicken breasts, 4 cups chicken stock, and smaller amounts of other ingredients to make 4 servings of soup. In this case, the 4 servings of soup are the products, and all the ingredients listed here are the reactants. Remember, chemical equations by themselves only tell us how many moles of reactants form a certain number of moles of product. We need stoichiometry to tell us how many grams or kilograms of reactant we need to form a desired amount of product. Stoichiometry's usefulness comes from its ability to express the relationships between the amount of reactant and the amount of product using molar ratios. We might remember from our math classes that a ratio is a numerical relationship between two values. For example, let's say we have a pizza that can be sliced into 8 decently sized slices. This means that the ratio between the number of pizzas and the number of slices is 1 to 8, which can either be written as the fraction 1 over 8 or as 1:8. Now, if 1 pizza can be sliced into 8 slices, 3 pizzas can be sliced into 3 times 8 equals 24 slices. All we had to do was multiply 1 over 8 by 3 over 3 to get an equivalent ratio for 3 pizzas. This should be part of the prerequisite for studying general chemistry, so I'm not going to review ratios in detail. But if you need clarification on that, I'd recommend watching another video or opening a math textbook to get this concept down before going any further. Molar ratios are interesting and all, but on a practical level, the utility of stoichiometry really becomes obvious when we convert molar ratios into mass ratios. Mass ratios tell us how many grams of a specific reactant are needed to produce a certain mass of a specific product. This is very useful for chemists, obviously, because it's often necessary to produce, say, exactly 100 grams of a certain chemical in the laboratory, and stoichiometry allows us to know exactly how much reactant we will require to produce this 100 grams of product. At the end of the day, stoichiometry tells us 4 things. Firstly, it tells us what reactants are needed. Secondly, it tells us what products will be produced. Thirdly, it gives us the amount of reactants needed in either grams or moles. Fourthly and finally, it tells us the amount of products yielded, again, in either grams or moles. When it comes to using stoichiometry, 5 major steps are involved. The first step is always making sure that the chemical equation in question is balanced. It's important to emphasize this point, because if we have a chemical equation that is imbalanced, our stoichiometry will give us the wrong amounts and bad things can happen. So, always make sure the equation is balanced before doing anything else. Our second step is to note down all the quantities that are given to us, either by the problem or by the quantities available in the laboratory. Our third step is determining which quantities are unknown, the quantities we need to solve for. Our fourth step is to construct the molar ratios relating the substances of interest to one another. Our last step is to solve for the unknown quantity or quantities using our molar ratios and given amounts. We'll look at the specifics of the problem-solving process once we get to our example problems. But first, for all the visual learners out there, this is a diagram which represents the steps we just went over. We'll call this the stoichiometry roadmap. The way this works is, we start at the circled S and end at the circled F. Let's start over here on the left-hand side of the screen. We have two substances, A and B. If we have the mass of A in grams, we can use the molar mass of A to convert this quantity into moles. We then look at the coefficients from the balanced equation to make a molar ratio, and we use this ratio to calculate the moles of B. We can either stop there, or if the problem is asking for the mass of B, we go back to the second step and use the molar mass of B to convert this value into grams of B. The molar mass of a substance is something we talked about last time, but as a quick refresher, the molar mass tells us how many grams of a substance comprise exactly 1 mole of said substance. Larger molecules typically have a larger molar mass, and molar mass itself is expressed in units of grams per mole, or G/mole. Before we move on, it should be noted that the numbers in stoichiometry problems usually vary a little bit depending on how different people round values. For example, the molar mass of lithium chloride is 42.394 grams per mole. When it comes to using this value in a stoichiometry problem, however, some people might round this to 42 grams per mole, others might leave it at 42.39 grams per mole, and still others might round it to 42.4 grams per mole. Based on which value is used, the final answers are going to differ, so don't worry too much if your answers to our example problems aren't exactly the same as what I write down. So long as they're close, the small variation shouldn't matter. Let's do an example problem. Example 1 says, the combustion of propane in the presence of oxygen occurs via the following reaction. C3H8 plus O2, both as gases, react to yield CO2 and H2O, both of which are also gases. How many grams of carbon dioxide are released when 10 grams of propane are burned? For this problem, we're going to designate propane as substance A and carbon dioxide as substance B. This is a combustion reaction, which, if we remember from last time, is the technical term for the burning of a substance. Propane is a hydrocarbon, a type of fuel produced via petroleum and natural gas refining. Like most fuels, burning propane produces carbon dioxide and water vapor, as shown by this reaction. With this background information in mind, let's go through our steps. We begin by balancing this chemical equation. Carbon, hydrogen, and oxygen are the three elements involved on both sides of the equation. We can go ahead and write a system of equations for these three elements. Propane has 3 carbons, so that's 3A. An oxygen gas and water both have no carbons, so all that's left is the 1 carbon atom in CO2. Our equation for carbon is therefore 3A equals C. Next we have hydrogen. A equals 2D. Then we have oxygen. 2B equals 2C plus D. If we solve all these equations in terms of A, we obtain B equals 5A, C equals 3A, and D equals 4A. This means that our balanced chemical equation is C3H8 plus 5O2 equals 3CO2 plus 4H2O. From here, we need to note down our given quantity, which is 10 grams of propane, and our desired quantity, which is X grams of carbon dioxide. Propane was our substance A, and we have this value in grams. So we first convert this into moles by multiplying 10 grams by the molar mass of propane, which is about 44 grams per mole. One mistake people often make at this stage is multiplying 10 grams by 44 grams per mole, which is incorrect. We need these grams units to cancel out, so we actually multiply 10 grams by the inverse of the molar mass, which would be 1 mole over 44 grams. From this, we get 0.227 moles of propane. We now need the molar ratio of carbon dioxide to propane, and for this we look at the stoichiometric coefficients in our chemical equation. The coefficient of carbon dioxide is 3, and that of propane is 1, so the ratio is 3 moles of CO2 over 1 mole of propane. By multiplying our moles of propane by this molar ratio, the moles of propane units cancel out, and we obtain 0.681 moles of CO2. Our last step is to convert this value into grams of CO2, which we accomplish using the molar mass of CO2, which as a matter of fact is also 44 grams per mole. We don't need to multiply by the inverse this time, since we want the moles to cancel out. So we just do 0.681 times 44 to get 29.96 grams of CO2. So, we can say that burning 10 grams of propane produces 29.96 grams of carbon dioxide. And that's all there is to it. While we're here though, let's try something else. Let's say we have 10 grams of propane we're wanting to burn. How many grams of oxygen would we need? This little bonus question is asking us to find the amount of one reactant given the amount of the other reactant, but the underlying concept is exactly the same as before. We first designate propane as substance A and O2 as substance B. We've already converted the grams of propane into moles and gotten a value of 0.227. All we need to do from here is multiply this by the molar ratio of diatomic oxygen to propane, which, looking at our coefficients, is going to be 5 moles of O2 for every 1 mole of propane. We can actually shortcut our way through them by adding the molar mass of O2, 32 grams per mole, over here on the right. Thereby making this a one-step problem. If we multiply across these three numbers, we obtain 36.32 grams of oxygen gas needed to burn 10 grams of propane per this combustion reaction. One more. Example 2 says, combining calcium sulfide and hydrobromic acid yields calcium bromide and hydrogen sulfide. If 240 grams of hydrobromic acid are reacted, how many grams of hydrogen sulfide are produced? This is a standard stoichiometry problem comparing amount of reactant to amount of product. But that's a lot of words we just looked at, so let's try and translate this mess into a chemical equation. Our reactants are calcium sulfide and hydrobromic acid. From what we know about chemical nomenclature, we deduce that calcium sulfide has a formula of CaS, and that hydrobromic acid is a binary acid with the formula HBr. We turn now to our products, calcium bromide and hydrogen sulfide. Calcium bromide has a formula of CaBr2, and hydrogen sulfide is H2S. Again, if you are at all confused as to how we got these formulas from these names, please go back and watch Unit 2 Video 4 on chemical nomenclature. It'll help a lot. Now to balance this equation. We could go ahead and write out a system of equations for calcium, sulfur, hydrogen, and bromine, but if we look closely at this equation, we'll notice that if we just add a coefficient of 2, to HBr, we end up with an equal number of all atoms on both sides of the equation. 2 calcium atoms, one calcium atom on both sides, and 2 sulfur atoms, that's already balanced. For a hydrogen and bromine, adding the 2 in front of HBr gives us 2 hydrogens and 2 bromines on both the left-hand and right-hand sides. So in this instance, trial and error was actually a faster method than going through the algebra. We don't really care about what states of matter these substances are in, so we're done for this part of the problem. We now move to the stoichiometry itself. Hydrobromic acid is our substance A, and hydrogen sulfide is our substance B. We convert 240 grams of hydrobromic acid into moles by multiplying it by the inverse of the molar mass of hydrobromic acid, which is about 81 grams per mole. We get 2.96 moles of HBr. According to the coefficients from our equation, the molar ratio of H2S to HBr is 1/2. When we multiply these two, we get 1.48 moles of H2S. Our last step is to multiply 1.48 by 34. which is the approximate molar mass of hydrogen sulfide. The final answer is 50.32 grams of hydrogen sulfide. It might have been noticed that most stoichiometry problems can be conveniently solved using this equation. We divide grams of A by the molar mass of A to get moles of A. We then multiply the moles of A by the ratio of B over A to get the moles of B. We multiply the moles of B by the molar mass of B to get the grams of B. This is the general framework for using stoichiometry, whether we're comparing reactants or reactants to products. And remember, A and B are interchangeable in this formula so long as we interchange them everywhere. We should also keep in mind that it doesn't matter what A and B are. They can be any two reactants, any two products, or one reactant and one product. It doesn't matter so long as we can make a molar ratio relating them to one another. In the next video, Unit 3, Video 4, we will introduce ourselves to limiting reactants. Thank you for watching.